SVXR, I started this with my co-founder Scott about 6 years ago, but actually been thinking about this problem for more like 12. And the idea that the important innovations in electronics today are coming more from packaging than they are from traditional shrinks at the transistor level. And so, you know, if you realize that's going to be important, then you need to be able to inspect all these thousands. Now we're actually approaching about 1 million connections inside a single package. So the number of connections, you know, some people say that's following Moore's law. I don't know if it is, but it's certainly increasing exponentially over time. Now, why is that important? Well, reliability in electronics, of course, is critically important. Here's Mr. Toyota from Toyota. And, you know, they were having acceleration. So CEOs don't like being called up before Congress. So at the highest level, that's why you need to make sure that your packages and electronics are 100% reliable. Does anybody know what the false or the defect rate is for electronics that goes into a car? How many parts per million or parts per billion? The answer is 0. It's not it's not per anything. It is just 0. You are not allowed to have a single defective part that goes into a car. And I've heard the case, somebody said that at Tesla, if you have a bad package or a bad on a board, they will scrap every one of those package, not only the package, but the whole assembly. They will scrap all of those in that lot. So if there's a bad package, they, you know, maybe that sells for $100. It goes on a board that's $2,000, and they may scrap 100 of those if they find a bad part. So it's really serious. So these guys are all very sad, and they don't like this. Now, where have we come in packaging? Well, obviously, things have progressed a lot in the last 50 years. So this is an example of a recent this is a CoWoS part, and there's a stack of memory die here, an application processor, and then this is the substrate. Probably many of you have seen things like this already. These individual die here are about 50 microns, which is thinner than a sheet of paper. And there's probably something like 5,000 solder connections between each of these die here. And then those are 20 micron copper pillar bumps. And this whole package, there might be 4, or I've seen a recent presentation, publication from TSMC. They're now putting 2 of these, 2 application processors and I think 8 of these memory stacks in one package. So, you know, those are going to be 1 million or more solder connections. How do you inspect these to make sure that the quality is okay? You know, this is an example of the kind of thing you might want to try and look for. This is between the silicon interposer and the substrate. The cracking here is caused by a thermal mismatch. And, you know, they work these out, but it's just like Moore's law. Every time they fix a problem, then, you know, I think maybe even faster than Moore's law, 6 months, certainly less than a year later, there's a new package coming out that has tighter, you know, trying to put more connections in that package. So it is driving technology the same way that Moore's law used to drive technology. I say used to, it's slowed down a bit on the front end. So this number, we're looking at something like 500 billion advanced packages per year that could need inspection. So that's a huge need. And the problem is that there aren't really any tools in the field today that are used as plan of record that can detect these problems in solder joints at the speeds that are required to inspect that kind of a volume. So one of the fundamental issues in process control, of course, is if you can't see it, you can't fix it. And if you want to control it, you need to measure it. KLA is founded on that principle, certainly. And the question is, how do you detect solder defects in these packages? Well, you know, we can do cross sections, we can do X-ray, we can do acoustic microscopy, all of those things. But do they meet the requirements that you need for process control? Well, cross-sectioning, of course, is kind of a gold standard. It'll tell you exactly what's going on, but it's very hard to sample at a high enough rate, and of course it's destructive, so you're not going to do 100% sampling. These are examples of the kind of defects that you might want to look for. Here's a good solder connection, the void. This is called a head and pillow. Sometimes this is called a non-wet as well. I think it's called a head and pillow if it's at the BGA level, and a non-wet if it's inside the package at the microbump level. They're pretty similar. This is a non-wet. All of these kind of defects here would test electrically good. You would not find them with an electrical test. These defects here, an open or a short, you could presumably find electrically, except remember there's a million connections, and you know, a small fraction of that actually goes to the outside. So you may not be able to detect these even electrically. For one thing, there's a lot of redundancy. So if it occurs, you know, an open will be might be compensated by the next ball over. So you really have a hard time measuring what the quality is of these packages. Now, electrical tests can't find these. It may or may not be able to find these. It's kind of intermittent. But you know, it's a go, no-go test. It doesn't tell you what the quality of the joint is. Optical inspection just can't see any of these because, of course, you're looking at something that's between two layers. And so if you can't penetrate those layers, then you can't see what's inside. And then you know, X-ray, I say SVXR, but any X-ray can find these. And the question is it good enough? Now, just to confirm this, we have been doing some work with Broadcom over the last couple of years, and you know, they went through and confirmed, yeah, 2D system can detect these kind of electrical defects. Well, the kind of X-ray tools that are out there today are in these three quadrants here. There are definitely high-resolution 2D and 3D tools that can see these kinds of defects. The question is, are they fast enough and automated enough to do it at a high sampling rate that you need for process control? The answer is no. On these tools right here, you might be able to do typically one die. If you could do a few die an hour for these large packages, you're doing well. You know, inline speeds need to be kind of like 5,000 parts per hour. There is an automated tool in X-ray, and probably a lot of people here are familiar with the use of X-ray in PC board inspection, PCB assembly. In those cases, there's a company called Vitrox, and there's others. It really started with HP, with the 4D product that they had. And you know, it's like a KLA tool, but it's for PC boards. And it looks to see are all the components on there. It looks to see if the solder connections are good. So why can't you just take one of those and use it on a package? Well, the problem is the resolution. These are great if you're dealing with these parts where things are 50 microns and up. There's a kind of a good rule of thumb for imaging, which is each factor of 2 in resolution gets you about a factor of 10 in throughput, meaning if you make the resolution a factor of 2 better, your throughput goes down about a factor of 10. It actually can be even worse than that, but it's pretty brutal. So if you want to go from 25 micron to 2.5 micron, that's going to be almost 1,000 times slower throughput. And because of that, you cannot directly take one of these machines and just tweak the resolution and run it. You have to come up with something new. And so that's what we've done at SVXR, is develop a new X-ray technology that is really fundamentally different than any existing X-ray technology for imaging. And it's roughly between 10 and 100 times faster than what's out there today. So I'll talk a little bit about that. Generally speaking, so a traditional X-ray system is shown here on the right. And it's a point projection microscope. So, if you've ever done shadow puppets where you have a lamp or a flashlight and you put your finger in front of it or hand and it gets projected on a wall, that's the way a traditional X-ray microscope works. And in that case, the resolution that you get at the sample is the spot size of the X-ray source. It's a little like a pinhole camera. So if you want, let's say 1 or 2 micron resolution, this X-ray source needs to have a 1 or 2 micron spot. Now, the way X-ray tubes work, they take a beam of electrons at high voltage and they shoot it into a target. And so that limits the amount of power that you can put into that target, because if you have a 1 micron spot, you try and put in more than 1 or 2 watts of power, you melt the target, even if it's tungsten or molybdenum or a high, refractory target, you'll just melt it. So there's a kind of a fundamental material science limitation to how much power you can get out of that system. In our case, what we did is invented a new type of imaging where the resolution mostly comes from the detector, not from the source. So in our case, we can have a 100 micron X-ray source with 1,000 watts of power, and we can get a micron. We've even gone down to like half a micron of resolution. So our resolution is determined from the detector, not from the source. And the advantage of that is we can increase the power here tremendously. So we run at about 1,000 watts of power. So it's somewhere between 100 and 1,000 times the power of say, a normal X-ray imaging system with a similar resolution. We also, we had to design this X-ray source. The other thing is we designed and built a detector, and our detector has a much larger area. It's about 10 times the area of a normal X-ray detector. So typical X-ray detectors are between 1 and 4 megapixels. Our system is about 30 megapixels. And we actually have a roadmap to go up to about 150 megapixels. This is designed for very high throughput. Now, I'll say one thing here. Let me tell you what it's not, what our tool doesn't do. It doesn't do review. It doesn't do what these guys do here. I don't know if anybody here is from Zeiss or Dage or Exelon. Those are all great tools. They're very good for looking at defects. In the front end world, we have inspection tools made by KLA in a lot of cases, and we have review tools. KLA makes a review tool, Applied Materials makes a review tool. Those are different things. We are not a review tool. We are not competing with these guys. We're really almost, you'd say we're competing with these if they were at higher resolution. So if you have one of these two, 3D tools, that's great because we work together with those tools. Here's just a comparison of our performance versus one of these PCB inspection tools, and this is a Dage. similar for other review tools. So, you know, we run at about 1,000 watts, 30 megapixels. We can do about 5,000 units an hour throughput, and that's 100% coverage on every part. And so that's great. I spent 10 years developing that technology. We got it working, and then you go to a customer and you say, hey, look, I can do this, and you show them a picture, and they say, well, our Dage tool or our Zeiss tool or our Exelon tool, they take much better pictures than you. And you know, then you say, well, but we go really fast. And they say, well, it's hard to convey speed in a PowerPoint. You know, what are you going to do with? And then there's another problem, right? So we're inspecting about 10,000 solder connections a second. Well, you need a lot of AI software in order to be able to process that data. We generate about 50 megabytes of data every few seconds. So that's kind of the next step in this. So here I'll walk you through. Can you see this all right, or should we turn down the light? It's okay. So this is a field. This is one field of view of our tool, 30 megapixel. And so zooming in on a single part, this is a non-wet test vehicle. And so it's program defect test vehicle that we had made specifically for us. There's about, I don't know, this one, I think it has about 40 or 50 solder connections. These dark connections in the middle are the solder connections that we want to inspect. So the first thing our tool does is, after you create the recipe, it goes in and it automatically finds all of those solder connections that need to be inspected, because they move around. Back end is not as well controlled as the front end is. Front end things are, you know, if there's any difference, then that's a defect. The back end, there's a lot of variation, and it's not really a defect, it's just a variation. So we got to find all these things. And then we make somewhere between 20 and 50 measurements on each of those solder connections. We measure the diameter, and we measure the solder volume and the eccentricity and all of that stuff. And then we come up with a number which we call the quality of the solder joint, the solder quality. And those should all be, you know, in a well-defined range. Now, this is just going through multiple test samples, and you can see the numbers changing. The part, it looks the same, but they're actually different parts. And you can see every once in a while, you get one where there's a lot of red flags. So those are outliers. There's something wrong with those solder connections. And we can do that in almost at the speed that it was running here. About a second or two, we can do that. Now, if you look at our image, you don't see a human. So one important thing, our images are not designed for humans to look at. They will not look nice. You won't be able to see a pretty picture of the defect. But that's not the point, because we're not trying to show pretty pictures to tool operators. We're just trying to find the outliers, the defects. And so in this case, the top-down view, you know, you maybe, if you're a trained eye, you can see it, but you certainly can't do 10,000 of these per second. So if you want to verify it, this goes back to the review tool. You take your nice 3D review tool and you go in, because now you know where to look for the defect, and you can use your 3D tool to take a cross-section and see where what the defect is. So here's examples of, this is a bad, these are bad solder connections, these are good solder connections, and you can see the difference. These are wet, the solder is doing what it's supposed to, and these guys over here are barely touching. These might all pass, they probably would all pass electrical test. So we do.
Are you rotating the sample then?
No, we don't need to do that. No. Yeah. You know, but these are not our images, right? This is what you get from a CT scan, right? Our images, what I like to say is, we want to take the worst possible image that we can and find the defect. Okay, so this is what you show to your boss, and you put in the paper. This is what our algorithms are looking at. So we get a heat map that shows you the good. These are special test die, so they have a range of good to bad on them, and you can clearly see. These two rows correspond to the top two rows in this part here, serial number 2, and you can see they go from good to bad, and clearly in the nice 3D CT cross sections you can see a variation from good to bad. And then you can do all your SPC stuff that you want to do with it. Here's a more challenging part. This is a CoWoS part. And again, it has an application processor in the middle and 4 memory stacks here. And we're inspecting, in this case, we're inspecting this layer right here, layer 3. It's about a 40, I guess it's probably somewhere between 50 and 100 micron diameter solder bump. And some of these that we look at have 25,000 of those, which is the connection between this interposer and the laminate. So the first thing we do is we go in and we find all of the solder connections that we want to look at. So here's a map of all of them in that die. And then after we do that, we take the X-ray image, we look at every one of those solder connections, make these 20, 30, 40 measurements, give a score to every single one of those pins, and then you can come up with a heat map of those 25,000 solder connections that tells you where the hot spots are. Typically they're in the corners, but they can be anywhere. So we're doing 100% inspection on these 25,000 solder connections in, 10 seconds or something. This is interesting. This is kind of takes it to the next level. Previously, that was just looking for kind of needle in a haystack defects. If you have an isolated random defect, like a solder ball in the wrong place or missing solder or something. This is about process control. So working with our partner, they did a DOE with 3 different lots. So first, they did there's a lot here, which is the plan of record. So, the way that you make these solder connections is you put your solder paste down, you do pick and place for all the parts, and then you put it in an oven and heat it. Now, one of the things that this customer had done is they correlated variations in the process with failure rates in the field. So when they get parts back from Apple or whoever their customer is, and they do the FA on it, they've been able to trace that back to a minor change in the process. So for example, before they put the parts in the oven, instead of putting it in within an hour, they left it out for 2 hours or 3 hours. Or when they ran the oven was 20 degrees hotter than it should have been. Small variations. You would never detect these electrically. There's no way to detect it in the factory. But what we do is we look at all of those solder connections like this, and we have a machine learning algorithm that can look at the kind of fingerprint, the overall result from that from that processing, and can tell you, okay, that part was left out longer than it should have been, or these parts were run at a slightly higher temperature. So we can provide really detailed feedback on the process. I imagine, our vision is that we'll be able to tell you which process tools that part came through. So if you have, a tool that's not performing as well as the rest, we'll be able to identify that pretty quickly. So I'm just concluding. This is my last slide here. It's a box. I have to give credit. Owens did a fantastic job manufacturing this. And the tool is actually being used in production at this time. You know, we think we have the first tool here that can perform an inline inspection and provide the process control and defect detection that packaging, especially advanced packaging for important critical reliability requirements like automotive, even cell phones, you know, have a lot of reliability requirements. So the technology that we have, which is this combination of high-speed imaging and machine learning, is, you know, we think it's the first tool that's able to really bring inline process control to this industry. And that's the end of my talk. Thank you.